The universe is 13.8 billion years old, and in a normal human lifetime, almost nothing in the night sky seems to change. But near a black hole, those 13.8 billion years can collapse into your final few minutes. While you're falling, entire galaxies can live and die outside. What would your last breath look like if it stretched across the age of the universe? To find out, you first have to understand what you're really falling into. Because the way this object is born decides how your time, your body, and even your information will end. Once it was a star. Not a calm star like our sun, but a giant, dozens of times more massive, burning fuel at a furious rate. For millions of years, it balanced two forces, fusion pushing outward, gravity pulling inward. As long as those matched, the star survived. Then the fuel ran out. Fusion stopped, the outward push vanished. Gravity finally won. The core collapsed in on itself. Atoms were crushed, matter squeezed into forms that don't exist anywhere on Earth. If the star was massive enough, that collapse didn't stop with a dense core. According to our equations, everything fell toward an unimaginably tiny region, a singularity, where density and spacetime curvature become extreme beyond comprehension. Around that singularity, the universe draws a boundary, not a solid surface, but a point of no return. Once you cross it, no signal, no light, no rocket can ever bring you back. That invisible boundary is the event horizon. From far away, a black hole looks simple, a dark circle that only cares about a few numbers, its mass, its spin, its charge. It doesn't seem to remember what it has swallowed, stars, gas, planets, or you. But if all that detail is truly erased, it breaks some of the deepest rules in physics. Hidden in that simplicity is one of the biggest paradoxes we know. And you're about to fall straight into it. Imagine you're in a small ship, drifting toward a supermassive black hole, millions of times more massive than the sun, like the one at the center of our galaxy. Out here, everything feels normal. Your cabin hums softly, your watch ticks, your heart beats once per second. You and a distant observatory sync your clocks. At the beginning, they march together perfectly, but as you gradually fall closer to the black hole, something starts to drift. Einstein's theory of general relativity says gravity is the curvature of spacetime. Where that curvature is strong, time itself runs slower. This is gravitational time dilation. From your point of view, nothing changes. Your seconds feel like seconds. Your body obeys the only rhythm it knows. But from the observatory's perspective, your clock begins to lag. A second for you takes a little longer for them, then a lot longer. You look at their clock on a live feed. It seems to race. Years flash by while only a short time passes for you. Headlines change, technology advances, stars shift their positions. The outside universe is accelerating away from your timeline. From their side, your signal tells a different story. Your movement's slow. Your voice starts to drag out. The last wave of your hand stretches over more and more of their time. Your image turns redder and dimmer as your light fights its way out of the deep gravitational well. To them, you're falling in slow motion. To you, you're just falling. You're not only falling through space anymore. You're falling into someone else's future. As you get closer, the view outside your window stops making ordinary sense. Stars don't stay where they should. Constellations warp. The black hole isn't just black, it's a violent distortion in the sky. Light, which normally travels in straight lines, is being forced to follow curved paths. Rays from stars behind the black hole bend around it, wrapping into arcs and rings. You might see a halo of light circling a completely dark center. Some stars appear duplicated, their images smeared into thin streaks. There is a region called the photon sphere, where light can orbit the black hole. Photons flying past with just the right angle loop around it like tiny satellites. Some escape after a turn or two, others spiral inward and vanish. From your seat, the universe looks folded. The background becomes foreground. The same star shows up in several places at once. Even your sense of direction starts to feel unreliable. And while your eyes fight to make sense of this warped sky, gravity quietly starts working on something far more fragile, your body. Gravity doesn't pull equally on all parts of you. It grows stronger with proximity. Near Earth, the difference between your head and your feet is tiny. Near a black hole, that gradient can be brutal. If you're falling feet first, your feet are closer to the black hole and feel a stronger pull than your head. At first, the difference is too small to notice, but as you descend, meter by meter, it grows. Your body begins to stretch. At first, it's a strange heaviness in your legs, then a tension along your spine. Eventually, the tidal forces become extreme. Your skeleton strains, your organs are pulled. If the black hole is small, the difference in gravity between your head and feet becomes so huge that the bonds holding your atoms together are overwhelmed. You are drawn out into a long, thin strand. This is spaghettification. You become a piece of cosmic spaghetti. In a small black hole, this would happen before you ever reach the event horizon. You'd be torn apart outside, never crossing the boundary in one piece. But in a supermassive black hole, the gradient at the horizon is weaker. Your whole body feels a powerful pull, but the difference from head to toe grows more gently. That means you might actually cross the event horizon intact. And even as your body starts to lose the fight, the most important line you cross is one you can't feel at all. You won't see the event horizon. No glowing ring appears when you touch it, no alarm, no visible edge. From your perspective, there is no sharp boundary. There is just more falling. One moment, escaping is still theoretically possible. The next, every future you could ever have now ends at the singularity. From the outside, though, that edges everything. It is the surface beyond which nothing returns. Light from just inside can never climb back out to reach the universe again. For distant observers, you never clearly cross it. You slow as you approach, your image freezing and fading over an immense span of their time. In their universe, you hover at the edge forever. In yours, that moment came and went long ago. Inside, spacetime is so warped that the roles of space and time start to blur. Outside a black hole, you can't stop moving into the future. Time is the direction you're forced to go. You can choose where to move in space, but not whether to age. Inside the horizon, one of the directions in space effectively becomes like time. Falling toward the center stops being a choice, it becomes your future. You might still wriggle a bit sideways, spin around, but all those motions ride on top of an unavoidable drift inward. Every tick of your watch takes you closer. You cannot turn around, you cannot hover. The geometry of spacetime doesn't allow it. From this point on, away from the black hole is no longer an option in your future. The closer you get to the singularity, the more extreme that curvature becomes, until our equations predict infinities, infinite density, infinite curvature. Whenever infinity shows up in physics, that's a warning sign. It usually means our theory has broken down, not that nature literally goes to infinity. Somewhere before that point, we expect quantum effects to become important. Gravity has to merge with quantum mechanics. We don't yet know how. Follow your fall far enough, and you reach a place where our best equations simply fail. But even as our math falls apart in the center, another mystery is forming on the outside. Think about what you're made of. Every atom in your body was forged in earlier generations of stars that burned for millions or billions of years before Earth existed. They lived, fused heavier elements, died in explosions, and scattered their ashes into space. Those ashes formed new stars, planets, and eventually, you. When you fall into a black hole, all of that cosmic history goes with you. Classically, it seems to vanish. Two completely different objects that fall in, a person and a rock, could leave behind black holes that look exactly the same. Only the total mass, spin, and charge remain. The details are erased. But quantum mechanics says something different. Information, in principle, can't be completely destroyed. The exact quantum state of the world is never supposed to just lose pieces. So where does the information about you go? One idea is that it doesn't disappear inside at all. Instead, it gets encoded on the event horizon itself. As the black hole grows, its surface area increases. If you imagine that area divided into tiny patches, each tiny bit of area can store a little bit of information. In this view, everything that falls in leaves an imprint on the surface, like data written to a two-dimensional hard drive. A three-dimensional person falls in, but the information that described them is smeared out over a two-dimensional boundary. In simpler words, your body dies, but the universe might still be forced to remember that you were here. You don't survive, your thoughts and experiences end, but some deep, scrambled representation of what you were made of might remain for as long as the black hole exists. Black holes stop looking like simple destroyers and start looking like cosmic archives. Now bring all of this back to the moment that matters most, the very end of your fall. From your point of view, your final moments are short, maybe minutes, maybe seconds. Your heart thumps, your lungs fill and empty. You watch the darkness grow brighter around its edges. Then, somewhere along the path inward, consciousness fails. From the outside, your fall near the horizon has been stretched enormously in time. As you get close, time dilation explodes. The light carrying news of your journey has to fight harder and harder to escape, losing energy and stretching into longer wavelengths. To distant observers, you slow and freeze. Their clocks keep running. Their universe keeps evolving. While for you, only a little time passes. Out there, galaxies are colliding and settling. New stars flare and die. Entire civilizations might rise and vanish. The cosmos thins out. Dark energy drives galaxies farther apart. The night sky would be changing on timescales no human on Earth could ever witness directly. In principle, if you could somehow keep looking out and stay alive, you would see the universe around you speed up, events outside playing in fast forward, because your time is running slower relative to theirs. That's how one last breath can touch 13.8 billion years. Not because you live that long, but because your fall is stretched across that much of the universe's history from its point of view. You exhale once. Inside your cabin, that's just a second. Outside, that same second might overlap with the slow fading of starlight and the long decline of galaxies. Then it's over. For you, the journey ends in darkness and pressure, and then nothing at all. For the black hole, it's just another tiny change in mass, in spin, in the pattern on its horizon. If our best ideas are even partly right, some trace of you remains, encoded in the geometry of spacetime at the edge of the hole, and in the subtle ways it might one day release its energy back into the universe. So what would your last breath look like if it stretched across the age of the universe? From inside, it's a breath like any other, a handful of fading seconds at the end of a human life. From outside, it's a moment that reaches across billions of years of cosmic history. And somewhere on the boundary of a black hole, the universe may quietly write that moment into its memory. A black hole doesn't just end stories. It bends them, stretches them, and hides them deep inside spacetime itself. Your life is brief, the universe is ancient. Near a black hole, for a few strange moments, those two timelines touch, and neither one comes away unchanged.